So in my previous video, I gave you an introduction of what the inverse of a function is, mainly that it is the inverse operations in reverse order. You go backwards through the operations to get the inverse. And the inverse can be found by taking your x, y coordinates on the original function and switching the x and the y to get the new xy coordinates in the inverse. We're going to explore this concept with x squared plus 3. So hopefully you've written this down already. This function here is a quadratic. I know this from x squared. And the plus 3 is outside the function, so it moves up 3. So I know the original function would start at 0, 0, x squared. So I'm going to go up 3. And then sort of recreate my 1, 1 or my step pattern to get these coordinate points and draw my function. Now I've just finished sketching lots of quadratics and all the shifts on it, so I'm getting pretty good at drawing those. But I could have done a table of values also to help me find those points. So I'll do a quick table of values for this function, this x squared plus 3. I'm going to use the points -2, -1, 0, 1, 2. And I'm going to plug in these numbers into the function. I'm going to start with the easiest, plug in 0. So 0 squared is 0, plus 3 is 3, so the output would be 3. If I plugged in 1, 1 squared is 1, plus 3 is 4. And if I plug in 2, 2 squared is 4, plus 3 is 7. So that gets me first 3 points, but I know this is symmetric because when I take -1 and I put it into x squared, -1 times -1 is +1, just the same as if I put in 1. So -1 squared is 1, plus 3 gets me 4 as well, and -2 squared is +4, plus 3 is also 7. And so that reconfirms some of the points that I had already graphed on here. 0, 0, 1, 4, so 1, 4, 2, 7, 1, 2, 3, 4, 5, 6, 7. Did I do that right? 1, 2, 3, 4, 5, 6, 7. Yep. And -1, 4, and -2, 7. So I'll just get rid of that. That just helps you visually see those 5 points that I've graphed. So that is the original function. Now I'm interested in graphing the inverse. So from the previous video, I know the inverse is found by taking my x's and y's and switching it. So in this one, I switched all my x and y's. So let's do that for the inverse. So this now is going to be the coordinates of the inverse. So if my original was -2, 7, if I switch that, it's going to be 7, -2. Just switching the x and the y coordinates. If the first was 1, 4, if I switch that, the new coordinate of the inverse is going to be 4, -1. 0, 3 becomes 3, 0. 1, 4 becomes 4, 1. And 2, 7 becomes 7, 2. So this green table of values is a new function called the inverse. And it is all the x's and y's flipped. So let's graph these new points. So let's start with going 7, -2. So that means 7 is my new x value. So 1, 2, 3, 4, 5, 6. Oh, a little bit off my graph. -2. So there's a point right there. Next one is 4. So 1, 2, 3, 4, and -1. 0, 3 has now become 3, 0 right here. 4, 1, so that's 4, 1, 2, 3, 4, but now I'm at +1. And 7, 2, again, that's just a little bit off my graph. And I get those points. And you can imagine that all of the points in between would also get flipped. So some point here would get flipped to right here, and a point right here would get flipped to somewhere around here, and the point over here would get flipped to someplace around here, and something here would get flipped to around something there, and I could do that for all the points in between, and I would get then the graph of the inverse to look something like this. And that graph, if this was f at x, this is f negative 1 of x, the inverse of it, because your x's and y's get switched. And that kind of makes sense. Like I said, it really makes sense with this spot right here, 0, 3. This is this spot here. If I switch the x and the y, I get 3, 0, and I get that. And the x's and the becomes y's, and the y's become x's. And you get this shape of the inverse. And what it does is it looks like the original was reflected on the line y equals x. So what does the line y equals x look like? Well, it's just a line right here. It's not an asymptote. I'm just drawing like a reflection line. Maybe I'll choose a different color than red so you don't think it's an asymptote. Let's make it purple. So if you can imagine, if you took the top half of this graph and folded it along that crease, folded it along that y equals x line, the blue graph would map on directly onto the green graph because all of the y's become x's. All of the y's here get folded down and become x's, and all of the x's get folded across and become y's. So this folding over top of that imaginary line there, that y equals x line, is a good way to visually see what's going on when you're finding the inverse of it, because the x and the y values get interchanged or switched. So this is an interesting little example to visually see what's going on. Just do your table of values, switch your x's and y's, and that can get you a graph. An interesting question that we will talk about is the inverse, the green graph, a function? I know the original was a function, but was the inverse technically a definition of a function? Well, it's a new relation, but it fails the vertical line test. So in this particular case, the inverse is not a function. So just because you start with a function, when you do the inverse, doesn't guarantee that you will get a function, and this is an example. Sometimes it is. The inverse of a line is another line, which is a function as well. Some will and some will not be functions. But we'll talk about that later. So that's a good visual of what's going on, but we'd like to figure this out algebraically. Figure out what the equation of that green graph is. So I'm going to start with that original function, f of x equals x squared plus 3. Now, this notation is helpful, but if I'm going to switch x's and y's, this notation makes a little bit more sense. Okay, y equals x squared plus 3. So, if I want to figure out this inverse algebraically, the first step is to write it as y equals instead of f of x, because we're going to need to switch the x's and y's. Step 2, when figuring out the inverse algebraically, is to interchange x and y. So I'm going to draw this dividing line because I don't want you to think that the blue thing is going to be equal to what I'm writing in the green line next. I am actually taking the inverse. So wherever I see a y, I'm going to replace it with an x. And wherever I see an x, I'm going to replace it with a y. And this green algebra statement is the inverse of the blue. Okay? These are not equal. They are not equal. It's the inverse. That's why I've drawn that little line underneath there. I don't want you to think they're equal. It's the inverse. Now, this green equation is technically the equation for the inverse, but I don't usually have inverses or equations with x equals. All my equations have been y equals. So step 3 is to rearrange or solve, oops, or solve for y. So I want to take this green inverse and rearrange it so it's y equals whatever that function is, which means I need the y to be by itself. So if I've got y squared here, I have to deal with this plus 3. I need to get rid of it so that the y is by itself. So I'm going to subtract 3 from both sides, or take it to the other side, however your teacher would explain it. But this becomes x minus 3 equals y squared. That's a good thing, because remember, the first operation, or sorry, when I'm doing my function, it says plus 3, so if I'm doing the inverse, I should have minus 3. And now I've got y squared equals x minus 3. But I need to rearrange it so it's just y equals. So I have to do the inverse of squaring. Well, we should know that the inverse of squaring is the square root. So after I take away 3, I need to do the square root of whatever that answer is. That would be going backwards in our original function. So this looks like the equation of the green graph. But if I was to actually draw this, and since we're in the middle of doing this sketching, this is a root function, and it's been moved right 3. So if I was to just draw this over here, I would have it right 3, but I would only have that. That is what the root function looks like. And I know that the picture actually looks like this. So explain to me why, when I take the square root, I only get half of it. Well, I've actually forgotten something. When I take the square root, there are actually 2 answers. There is a plus answer and a minus answer. So remember, if I ask you technically, what's the square root of 25? Most of us would just say 5, because 5 times 5 is 25. However, the square root of 25 could also be negative 5, because negative 5 times negative 5 also gets you 25. So technically, when you take the square root of a number, you should have a plus answer and a minus answer. Often we ignore the minus answer, but in this case we can't. We have to have a plus answer and a minus answer. And that's good news for our picture, because the plus answer is what you see there, but the negative answer would be outside the function and flipping it down. And it would get this second half of this shape. So this is the plus answer, this is the minus answer, and now we get a graph, that looks like the picture we already knew. So that's a good little thing to remember. When you take the square root of something, we need, in this case, to include the positive answer and the negative answer. So that is the equation of our inverse. Now, we usually don't write it with a y second. You probably would rather see it like this, y equals plus or minus x minus 3. That looks more like the equations for functions. But then I'm going to finish off with step 4. Step 4 is to use the function notation. So rewrite in function notation, which is f at -1 of x. And so the function is actually, or the inverse is plus or minus square root of x minus 3. And so that is the equation of the inverse, algebraically. And again, if we think back to the Celsius question in my last video, this function says take a number, square it, and then add 3. If I'm going to do it in reverse, I would have to subtract 3 first and do the opposite or the inverse of square root, which is squaring, which is square root. And you see then that this is the inverse operation. Take your number minus 3 and take the square root. And that is called the inverse. All right, let's try and find the inverse of another function algebraically. So here's example 3. Let's find the inverse of this linear function now, 3x minus 2. And we're going to do it algebraically. Okay, so let's start by writing the original down. And step 1 says put it in y equals so that I can see the interchange of x and y. Now I'm going to take the inverse. So that's why I'm drawing this line, because it's not equal. I'm taking the inverse now. And the inverse says I switch the x's and y's. So this is no longer a y, it's an x. And this x becomes a y, and we have that. That is an equation of the inverse, but it's not written the way we like to see it. We need to rearrange this so we get y by itself. You see we have minus 2, so of course the inverse of that is plus 2. So taking the negative 2 to the other side does the opposite operation. And if I want y by itself, I then have to divide by 3. There's no plus or minus in this one because I'm not taking the square root. It's just divided by 3. And that is technically the answer, but I want to write the answer with this notation because it does ask for the function notation of the inverse. And so it's x plus 2 over 3. And we have found the function notation for the inverse of 3x plus 2. Again, think about this. If we were actually to do this operation, here's the function. Take a number, triplet, and minus 2. If I'm going to go backwards, I have to do plus 2 and then divide by 3. Plus 2 and then divide by 3. And there is that. Now, although we can probably figure this out by just doing the inverse operations, reverse operations in our head, this process is going to be helpful when the functions get more complicated, so I want us to practice this process. So there's 2 examples, well, I guess 3 examples. In the next video, I'll show you a 4th.